Hey guys, okay, so let's go ahead and get started. Today will be a review for your first exam. So the way that this is going to work is I'm just going to pick problems that will be very similar to what will be on your exam. So if you're able to do the problems that I do today in class, then you should be completely fine on the exam. Okay. So the exam will consist of uh, sections from logic and from proof. So I'm thinking that there will be maybe 2-3 questions on logic, and then 2 to 3 questions involving proof. Okay, so, and when I say logic, I mean proofs with logic, and then proofs with simple number theory type of things. So let's look at a simple logic proof. So claim. Okay, so if P and Q are propositions, then say P and Q implies P is a tautology. Okay? So there's 2 ways to prove this. So I'll show you the first way, which is not, so this would be like proof for like 10 points. That's a 10. Okay, so you can use logical equivalencies and string these together. So we can say P and Q implies P is logically equivalent to, well, we can get rid of this conditional, and this will become, what is that rule? I call it star, I think, in my notes. Yeah, so this will be negation of P and Q, or P by star. So that star rule I pointed out several times in lecture. It's the easiest way to get rid of the conditional. So that is logically equivalent to that by star. Okay, so then the next step would be, well, I see the negation of a conjunction, so I can use De Morgan's law. So this will be not P, or not Q, or P by De Morgan. Okay, so then we can group these together in a different way. So we can say this is logically equivalent to not Q, or say not P or P by associativity. Okay. And then here, not P or P, right? At least one of these is going to be true, right? Because if not P was false, then P would be true. And if not P was true, then it's true. So we can say this is logically equivalent to, and that has a name actually, I think it is, the negation law. Okay, and then we have not Q or true, well, this is true by definition. And then we're done. Right, so this compound proposition here is always true, so it is a tautology. Okay, so stringing together logical equivalencies like this will give you full credit, but if you want bonus points, is another way to prove this. So if you want 15 points, you can prove this a different way. So this is a conditional statement here, right? So we only need to consider the case when the hypothesis is true, since otherwise it's true vacuously if the hypothesis is false. So we can say something like, suppose P and Q is true since, get a cat in the way, since otherwise P and Q implies P is true. And so if the hypothesis is false, then the conditional is always going to be true. So we're assuming the hypothesis is true because it's the only case that we need to consider. So then, if the conjunction of P and Q is true, then P must be true and Q must be true. Right? Okay. Then P and Q true implies P is true, and we are done. Right? Because then, if that's true, then that's true, and true implies true is true. Okay? So that would give you bonus 5 points if you were to argue with words rather than logical equivalencies. Okay? Okay, so let's do another one. Actually, I will definitely put a problem on there that involves negating statements. So let's say this is a good one. So find the negation of the statement for all x, for all y, x greater than or equal to 0, and y less than 0 implies x times y less than 0. Okay? So find the negation of this. Okay? Solution. So we negate this compound proposition. Y less than 0 implies x times y less than 0. Okay? So when we negate the universal quantifier, we get the existential quantifier. So this will be, there exists x, there exists y. So negate that, we get that, and that. And then we have the negation of all this business here. Yeah. All right, so keep on going. So we need to send in the negation into this statement here. So before we can do that, I need to replace this conditional by the OR operator using star, the star rule. Like that. Okay. Now we can send in the negation into this now using De Morgan. So this is by star. So the negation of the negation, so it's double negation law, cancels out. Okay. But then the negation here, using De Morgan's law, this becomes an and then we negate that statement there. Yeah. Oh. Y. And then one more step here. And the negation of being strictly less than 0 is greater than or equal to. And then we're done. Okay. That's an example of negating a compound proposition. Okay, so next, let's say claim. So maybe something like if in m are even, then n times m is even. Yeah. So, let's look at the proof here. All right, so we can do this with a direct proof. So we'll just say, okay, let n and m be even. So we make a declarative statement, and once we know that n and m are even, we can use the definition now. So then by definition, there exists integers, I don't know, k and l. So that n is equal to 2k and m is equal to 2l. Okay? Therefore, n times m is equal to 2k times 2l. And we need to make this look like an even number now by definition, so I'll just factor out one of the 2's. In fact, I'll just write it out like this. Yep. So we have n times n is twice of an integer, so we just need to state that this is an integer and then we'll be done. So since 2kl is an integer, n times m is even by definition. And then we're done. Yeah. Now, if you watched the previous lecture using LaTeX, these types of proofs I'm going to ask that you write up in LaTeX, and you follow the format that I posted in the last lecture. Okay. So let's do a few more of these, and we'll call it a day. So if n cubed plus 5 is odd, then n is odd. Okay. So here we can prove this. If we tried to go directly, we wouldn't have much luck. So we can do this in an indirect manner. Contrapositive, I suppose. So proof. And again, I'm writing these proofs out without any scratch work. All of you will probably need to have quite a bit of scratch work before you have the pieces necessary to write the formal proof. Okay, so by way of contraposition, so In order to do proofs by contraposition or proofs by contradiction, you really need to know how to look at the contrapositive of the statement. So the contrapositive of the statement is if n is even, then n cubed plus 5 is even. Oh, sorry. I knew that there was something off here. There. So if n cubed plus 5 is odd, then n is even is the original statement that I meant to write. So the contrapositive is if n is odd, then n cubed plus 5 is even. Okay? So I just had a mistake in the original claim. So by way of contraposition, suppose n is odd. And, so we have our supposition now. We can use the definition after that. So then, by definition, there exists an integer k, so that n is equal to 2k plus 1. Okay, that's just the definition of being odd. All right, so therefore, n cubed plus 5 is equal to 2k plus 1 cubed plus 5. Okay, so then we need to do some algebra here. So I'm going to do this in 2 steps, just because I always forget the cubic formula for products. So this will be 4k squared plus 4k plus 1 times 2k plus 1 is 5. Okay, so what does this become? This would be 8k cubed plus 4k squared. So actually, do this carefully here. 4k squared plus 8k squared plus 4k plus 2k plus 1 plus 5. Okay. So I suppose we can combine my terms, right? So 8k cubed plus 12k squared plus 6k plus 6. Now our goal is to show that this is even. So I see that there's a common factor of 2 amongst all these terms. So we can just take that out and we'll have what we need. So then we're almost done. We just need to state that that's an integer. We have twice of an integer, so that means that n cubed plus 5 is even, which confirms the contrapositive of the claim, so we're done. So we just have to say that now. So since 4k cubed plus 6k squared plus 3k plus 3 is an integer. N cubed plus 5 is even by definition. And then again. Okay. So that required a bit of algebra, but provided you have scratch work and you're working out the algebraic parts on the side, you should be able to fit all this together. Yeah, this proves contraposition plane, and we're done. Okay. Let's see. And actually, I probably should show you how to do this using LaTeX as well, that same problem. So if you had that written down, let me share my screen. Okay. And so this is what I opened up last time. So let's go ahead and do that proof that we just did again, but just this time in LaTeX. Subsection, call this problem 4 or something like this. So if n cubed, when you take powers, it's good practice to put those in curly braces. If n cubed plus 5 is odd, then n is even. Okay, so let's go ahead and write the proof now. Begin proof. Okay, so basically what I just did, but now I'm going to show you in LaTeX. So by way of contraposition, guess it doesn't recognize that. So by way of contraposition, suppose n is odd. Okay, so then by definition, there exists an integer. I can use set notation here. There exists k backslash n backslash math db z, so that n is equal to 2k plus 1. All right, so let's go ahead and compile this and see what it looks like. I'm going to go ahead and put this on a new page just to separate it out. So it's a new page. Okay. All right. So now we need to do the algebraic steps. So 4. So the easiest way to do this is just to come up here, just copy, paste, and then make the changes here. So in cubed plus 5 is equal to 2k plus 1 all cubed plus 5. Okay, so let's just see what that looks like. All right, so that line there is good. So now we need to fix the next line here. What did that become? It was 8k cubed plus 12k squared plus 6k plus 6. Okay, so now we need to put a new line here. So the way we do that is double backslash and then do ampersand equals. Now we just factor out the 2. So this becomes 4k squared plus 6, and that's cubed, plus 6k squared plus 3k plus 3, period. So we compile that. So then we're almost done. So since, let's say, 4k cubed plus 6k squared plus 3k plus 3 is an integer, cubed plus 5 even by definition. Done. So there's your proof. Okay. So, okay. So I don't think there's much more that I can do for you as far as like getting you ready, because all the proofs are going to be more or less like this, including the irrational proofs and the biconditional proofs that we did. So I guess what I'm going to do for you okay, so I'm going to all right, I'm opening up the homework again. Okay, to edit. And it will be open until this Sunday. Right? So for the rest of today, I guess, I would get caught up on all the homework that you might have missed. This practice is probably some of the best practice that you can have for your exam. And then next class, we're going to start a new section, but I'm also going to post the exam on Blackboard for you next class. And you'll have 1 week to finish it. Okay. So I guess that'll be it for today. Is anyone having any problems with using LaTeX? speak up now, or I guess everyone's good.
Yeah, I got a question. Can you walk us through like what we have to do for latex?
So you see how I've written these problems this way in LaTeX on this document here? So I guess what it'll look like is you'll say like exam one like portion, and then you'll put your name. And so I'm going to give you things to prove that involve integers and rational numbers, okay? So for example, if n is odd and n is even, then n times n is even, would be like an example. And then it's your job to make a LaTeX document, type in the problem, and then write the proof. Just like just exactly like I've done here. Okay? So not everything will be done in LaTeX, but I'm going to ask that you prove several things, maybe like 3 problems using LaTeX. And you have a statement, and then it's your job to type in the statement and then type out the proof using LaTeX. And then once you do that, you can export it as a PDF, just like this. And that will be what you turn into me. Does that kind of clear it up a little bit?
Yeah, yeah, that's cool. That's cool.
Oh, I wasn't sharing my screen, but let me, so just like this, right? So you'll have the problems and you type them in, and then what you'll do is you'll click on this little download PDF, and you will generate a PDF. So you have like exam one LaTeX portion, and then your name, and then you'll have statements that you prove just like this, and you should generate a document that looks just like this. Yeah. Okay, so I guess that'll be it for today. Again, I opened up the homework problems again until Sunday, so please, if you haven't finished those when you can. And then we'll meet again Thursday, or not, yeah, Thursday, and we'll start a new section on Thursday as well. It won't be on the exam, so it'll be new material. Okay? All right, that will be it. Y'all stay safe, and I'll see you Thursday.